All right, as we continue to talk about forces, I want to talk about situations where we have strings and tension, and then when we connect objects together. So when we have a string or a rope, there is a force that's conveyed through the string or rope between connected devices or connected objects, and we call that force tension. Now, tension is a force that acts in both directions equally. So if I have a string with a tension of 10 newtons, it's not that I have 5 newtons in that direction and 5 newtons in that direction. It's 10 newtons in that direction, 10 newtons in that direction. So if I were to put a force gauge in the string, it would just read 10 newtons in both directions. So that string can be used to convey one force from one object to another. And that tension is a form of force. So the book uses capital T, a capital T vector to represent tension. I sometimes say F sub T or things like that. You might see me do that. So tension is a type of force. It's measured in newtons, just like any other force. All right. And if the string is not tight, the tension is 0. All right. So when we have tension in a real world situation, it does vary through the length of the string. And in most of our situations, we won't deal with that. But if you look at this, we have 3 different spots on this rope that tension could be measured. One at the bottom of the rope, one in the middle, and one in the top. And those in hypothetical situations will treat them as the same. But technically speaking, the weight of the rope in a real world situation would cause the tension to be greater at the top. So when, for example, you're on a rope swing and swinging, the rope generally breaks right at the top because it's got not just your weight, but also the weight of the rope and everything else on it. So that's why a rope typically breaks at the top, because that's where more force is being applied. So in here, we're just going to, in general, treat ropes and strings and any connecting devices as a massless substance. So the tension between 1, 2, and 3 would be the same. But in real world settings, the tension at 3 is higher than the tension at 1 because the rope actually has a mass. All right. We use pulleys in different ways. In this case, a pulley is just a way to change the direction of the tension. So the person lifting is putting the same amount of force on the rope as the mass that they're lifting. We can use pulleys as a simple machine and make several loops around multiple pulleys and cause us to use less force. That's a very common use of a pulley system. And we might talk about that at some point in time, but generally we're just talking about pulleys in a way to change the direction of the tension so that the tension on either side of this is exactly the same. The reason we use a pulley in this type of situation is that we can use our own weight to assist us in putting tension on the rope to lift up a mass. Otherwise, we're lifting up just straight up without a pulley system. All right. When we connect objects, we can connect them either by having them pushed together and pushing on one and making the other object move, or by connecting them with a rope or a string. So the thing that keep in mind when we do that is that when they're connected, they have to move as one object. So their masses are combined into one mass, and we have to use F equals ma with the mass of the system of the connected objects. So their accelerations have to be the same, and we have to treat them as that. However, we got 2 objects, so you can see here, the hand is putting a force on the first object. The first object then is putting tension on the string between that and the second object. The tension on the string is the same. Now, both of these objects, assuming we have friction, are going to resist the force as well. So depending on the masses of the objects and different situations, we have to use individual objects to figure out the force that they're each being supplied with, but then we use them all as a system to get the overall acceleration and make predictions. So we treat them as separate systems. So if we look at the free body diagram of those two boxes, disregarding the vertical forces, the force to the right from the hand and the force to the left from the tension are unequal, so it's going to accelerate to the right, and the same amount of acceleration has to occur to the second box because they're connected, but the force to the right on the second box is all due to the tension from the rope between the two boxes. So that's our free body diagram on these two when we don't put in the vertical components as well. Now that comes into play in situations like this. All right, we got a pulley system, and it makes the change in direction there. So we have these free body diagrams. The mass 1 is sitting on the table with a normal force against it and a tension pulling it to the right. So in this case, as it says in there, it might be easiest to have the coordinate system follow the string. So we just made the direction the string is going, regardless of whether it's going to the right or vertically downward, as positive, and to the left and upward would be negative in that case. So what we would look at then is the combined mass of the two objects moving as one acceleration. So obviously, in a setup like this, we don't expect any. There are three different things that can happen. All right. One thing that we know is not going to happen is that it's not going to, mass 1 is not going to move to the left, and mass 2 is not going to go up. One thing that can happen is mass 2 is pulled down but not able to move because the friction on mass 1 is, the static friction on mass 1 is enough to hold it in place. The other situation is if mass 2 has enough force to cause mass 1 to break free and move at a constant rate, that means it's not going to accelerate. But here we have a situation pretty obvious. We have acceleration vectors that are in this diagram. And so mass 2 has enough force downward, which is the weight, to cause mass 1 to accelerate to the right. Mass 1 and 2 have to accelerate at the same rate. So if we do these free body diagrams and look at these, the force on mass 1 and 2, the overall net force, is equal to mass 1 plus mass 2 times the overall acceleration. And if we look at the forces on those, mass 2, the tension between that and the weight, we have to have for the force on 2, that's equal to the weight minus the tension, and force on mass 1 is equal to the tension minus any friction force. Now, it doesn't say that we have any friction force on this. We don't have a force vector, so we don't necessarily have any, but that means that mass 1 and mass 2 have to act as one full system to have the same acceleration. So the combined masses, mass 1 and 2, times the acceleration of the whole system. So that's our challenge when we do these systems. On Friday, we're going to do a lab on a Atwood's machine. And an Atwood's machine is a machine that has a pulley and two weights, one on each side, and we're going to calculate how rapidly they accelerate. Obviously, the heavier weight will accelerate downward. But if you look at that, it's not going to accelerate downward at 9.81. If you look at this system, the acceleration of M2 is not 9.81. It is the total mass divided by the net force, or divided into the net force. So they have to have the same acceleration. So that makes it a challenge for us to do. All right, so we'll do that on our lab that we do on Friday. Hope that helps. I'll talk to you on Thursday and Friday. We'll have a couple labs to do, and we'll figure some of this stuff out. Thanks a lot. See ya.